Our next speaker is Geraint Lewis, who is going to tell us about whether the cosmological principle is in trouble.
Okay, thank you. As was mentioned at the start of this session, it's important for us to consider our underlying assumptions in cosmology, right? We basically have a very successful cosmological model, but it's built on assumptions, and if any of those assumptions are truly sand, then we have to worry. So what I want to talk to you about today is the work that we've been doing on this question of the cosmological principle, which may be one of the most fundamental assumptions that we are making. So just to remind you what the cosmological principle is, right? When you do your Cosmology 101 class, the professor stands up and says something like, the cosmological principle says that the universe on some scale is homogeneous and isotropic. And then off they go and they start talking about something else. Now, we know that our universe, when we look at it in terms of galaxy surveys, etc., is clearly not strictly homogeneous and isotropic on every scale because we can see distributions of galaxies, we see voids and clusters, etc. But what we say is that if we take some sort of scale, and that scale is around 100 megaparsecs, and we average out the universe, then beyond that scale, our universe should be isotropic and homogeneous. The thing that's often not mentioned in your cosmology class is what that actually means. What it means in terms of what we do on a day-to-day basis is that the cosmological principle puts symmetries on the underlying metric in the universe, okay? So the Friedmann-Robinson-Walker metric is built starting on assumptions that come from isotropy and homogeneity. And so that's really at the very base of where we start with our cosmological model. But the question is the cosmological principle correct, right? Because if it's not, then we have an awful lot of work to do because we have to go back to the very basics of modern cosmology. Often what people do is they show a picture of like we've got at the top there of the CMB, and we say, look, the CMB looks pretty smooth. On scales of around 10 to the minus 5, it looks homogeneous. And so therefore, what we can say is that cosmological principle kind of holds. But of course, what we often don't talk about is the fact that the picture that we have up there on the top, that is the cosmic microwave background after it's been through a series of steps. Number one, of course, you have to remove a lot of the contaminants from the galaxy, etc. But the biggest sort of signal that's removed from the cosmic microwave background is the fact that there's an all-sky dipole, right? So we can see that this dipole is a factor of 100 larger than the fluctuations that we see in the CMB. And it's been known about since the 60s and into the 70s. And of course, what this is interpreted as is that this shows that we are not fundamental observers of the universe. We are not co-moving observers. We actually have a proper motion with respect to the Hubble Flow, and that's what we see as this dipole in the CMB. And so we have a motion of around 370 kilometers per second in the direction of the red that we've got there. That's good, right? The CMB looks like a nice example that the universe is smooth and isotropic once we have taken away this dipole. But the fact that we are not fundamental observers, the fact that we are not co-moving observers, means that our motion should be imprinted on our other observations of the universe. So we should be able to use other kinds of cosmological measures to check the cosmological principle. And essentially 40 years ago now, we had this really nice paper by George Ellis and John Baldwin, basically asking the question, right, if this interpretation of our motion with respect to the cosmic microwave background is correct, then what would the influence of that motion be on our observations of surveys of radio galaxies? And so what they basically said is that if we take a flux-limited sample, so we look out into the universe and we put a flux cut there, if we were a co-moving observer, then we would expect the number density of galaxies that we see across the entire sky to basically be the same, right? Other than shot noise, it would be the same. But if we are moving with respect to that sample, then we've got to consider additional relativistic effects. You clearly have Doppler boosting and deboosting in the opposite direction, so objects can appear brighter and fainter. You've also got the effect of aberration. So aberration means that the angular position of your objects starts to move. And essentially what you would have is that at the boundary of your survey, then you'd have these additional effects which would be moving objects into and out of your observational window. And essentially what they said is that what this should do for us is it should put a dipole into the counts of galaxies that we see. Okay? So the issue, of course, is that our velocity is small. It's 370 kilometers per second, so it's not exactly relativistic. But if you go through the numbers, you still expect there to be a sort of a percentage variation across the sky due to our motion. And there have been a number of people who have tried to test this, and over the years there's been some contradictory results. But things changed a couple of years ago with this paper by Nathan Seacrest, a test of the cosmological principle. Okay? So what's happened, of course, is, as we already heard, is technology is improving, our data taking is improving, and now we're getting huge samples of quasars, radio galaxies, etc. Samples large enough where we can beat down the statistical noise and see if we can measure our motion in terms of counts of galaxies on the sky. So they use CatWise, which is an infrared satellite. What you've got on the left is you've got the sky distribution of these CatWise quasars. Of course, in all of these surveys, the galaxy gets in the way. It's really annoying. Cosmology would be much easier if we were outside of the galaxy. But we lose a big part of the sky. What you're looking at there is the smooth number counts. And you can see that, firstly, that they're not uniform across the sky. And secondly, if you squint a little bit, you can see that there's an enhancement in the top right and a decrement in the lower left. Okay? Now, Seacrest et al., they analyzed this sample through a series of estimators trying to measure a dipole in this signature. And these are the results of what they find. So, does this work? There we go. The star there, that's the direction of the CMB. They find that dipole points in this direction. And so they get the directions kind of right. They say there's a dipole in the galaxy counts, and it's in the right part of the sky with regard to the CMB. The place where things start to look a bit dodgy is when you consider how big that dipole is, what the amplitude is. And from the CMB expectation, right, the dipole should be this number down here, what's that? 7 times 10 to the minus 3, okay? So a small effect. The amplitude of the dipole that they find is more than twice that, okay? And so they go through and they do a whole bunch of statistics, and they basically say that this is, essentially pushing a 5 sigma result, that the dipole in the galaxies is significantly different to the dipole you expect from CMB motion. Now remember what this means, right? Imagine we didn't have the CMB, and we were trying to find out our motion with regards to the Hubble flow from galaxy counts. We would infer that our motion is closer to 1,000 kilometers per second rather than 400 kilometers per second. So this result, essentially the test of the cosmological principle, there were suggestions that this means that the cosmological principle is somewhat broken. And so what you have to do, of course, is you can't just take one analysis. You have to let everybody else play with the data. And Seacrest et al. Released all the data, so we thought we would have a go at it. We took a slightly different approach. They took I have to be very careful with words here because religion comes into it. They took a frequentist approach, and we took a Bayesian approach to our modeling, okay? So we were interested in the parameters we derive and the uncertainties around there, and the Bayesian evidence which we can get for our hypotheses. So we did exactly the same thing. We took their data set, we defined a dipole model, etc. There was some complications. There's an ecliptic bias due to the way the satellite scanned the sky, etc. But effectively, we do what all Bayesians do. You define your likelihood, and then you run your likelihood through your Bayesian machinery, and you test various hypotheses. So what do we find? So if we concentrate up here first, let's do this, okay? So here's the CMB direction, here's the dipole direction as found by Seacrest, and there's our direction. And because we're doing the Bayesian approach, our uncertainties are around our measured parameters, and again, what you find is that these measurements are essentially all consistent. Of course, we get our other parameters, and the important one here is this one, which is the size of the amplitude relative to what you expect from the CMB motion. And the answer is that the dipole amplitude we find is almost 3 times larger than you would expect. Okay? So we sort of confirmed what Seacrest did, but you have to worry then, is it catwise? Does catwise have a dipole in there from something else, the way the survey was done or something, or the way the quasars were selected? So we decided to try another approach, and that was to try and get another sample of quasars, radio galaxies, etc. As we were doing this work, the Quire sample was released. So the Quire are quasars selected from Gaia, right? So you can use proper motion, color information to select these quasars. This work I did with Vasudev Mittal and Oliver, my PhD student, is in the audience and has a poster outside. So I recommend you have a look at his poster and ask him some questions. But this, again, is a large sample of quasars, right? There's 1.3 million of them. And we wanted to play exactly the same game again. Is there a dipole in this distribution of quasars? So this is the distribution of quasars you can see on the sky, right? And you can already see that we have problems. And the problem is, of course, is that, firstly, there's a non-uniform distribution. And secondly, those non-uniformities are correlated with the galaxy. And so what we are seeing are essentially, we got an optical survey here. It's the effects of dust, extinction, etc. But the makers of the catalog, Story Fisher and David Hogg, etc., they had provided selection functions, so we thought that we would go through and try and do the dipole measurement. We struggled for a while to understand what was going on, but we realized that at the end of the day, this sample is actually highly contaminated. No matter how well you think you are doing your dust corrections, if you want to do measurements of percent level stuff, your dust has to be known really accurately. So what we actually did is we fit 2 dipoles. So one in blue, that's what we call the contamination dipole. That's correlated with the galaxy. The other one in yellow, which is the residual dipole, that nicely points roughly in the direction of the CMB. Okay, so we were happy again. And we tried to think, how do we deal with this? Well, we couldn't do any better in terms of the selection function, so we did what astronomers always do when faced with difficult data, is you start to chop away the data you don't like, right? So we do cuts, and we try and cut away from the galaxy to try and get clean samples that aren't affected by extinction. So what you can see here, going from yellow through to blue, those are galactic cuts, right, in B. So we go from 0 up to 40. And what you can see is that this is fit in a single dipole. When we have no cut at all, our dipole is basically pointing towards the galactic center. We're picking up just contamination. But as we cut away, the direction of the dipole shifts. And it shifts towards the direction that you expect from the CMB, which is good. Across the bottom, you've got the amplitude of that dipole. So you can see that the amplitude is really strong for no cut, but as we cut away, the dipole amplitude falls, and it gets lower and lower. And so what we end up with at the end of the day is that when we cut away at 40 degrees, we actually have a number in there for the amplitude, 11 in these units, with big error bars, but again, it's more than a factor of 2 larger than we'd expect from the CMB. So the CMB expectation here is 4, but again, we're finding the dipole is larger. But because we've cut away so many objects, our error bars have blown out also. So what do? Well, you go looking around for another sample, right? And we did what a lot of people have been doing recently, is you basically try and deal with radio surveys. Of course, radio telescopes are unfortunately stuck to the ground, and so you tend to get surveys in either the northern or southern hemisphere. And what people have generally done, they've tried to take 2 catalogues and match them where they overlap, which is problematic because your 2 telescopes are different, the surveys are going to be different, etc. And if you get that matching wrong, what you've done is you've introduced a dipole into your signal, right? A northern hemisphere and southern hemisphere dipole. So what we wanted to do, again, is basically not do catalog matching. We wanted to treat these as 2 independent sets of data, work out the likelihood, and do our dipole measurement from there. So for the north, we used NVSS, and in the south, we used RACS. And as you can see, we've got roughly 400,000 objects in each. So we go through, and we play exactly the same game again. We start off by fitting a dipole to only NVSS and only RACs, and these are the directions and the dipole amplitude. The expected dipole amplitude is around, again, 0.004 to 5. The amplitudes that we are getting are more than double that, okay? So what do? We started to worry about local sources. What if there is local structure that is starting to impact our measurements? And effectively what we did is we did a cross-correlation between our samples. So we've got NVSS, we've got RACs, and we cross-matched with known redshift catalogues, okay? And you can see that in each of those samples, there's roughly 3,000 to 4,000 objects which are in that low redshift regime. So it's only 1% of the total, but if you look, I mean, you can see this structure here, right? It appears in RACs, you can see it across the sky. So we thought, okay, let's see the effect of that structure. And what we've got on this side, this is subtracting basically structure below the redshift on the bottom of that plot, okay? So you can see at the far side, we've got all objects, and as we move towards the right, we cut away, increasing the redshift. Now, it's kind of hard to see, but the actual dipole amplitude drops, and it drops by around 20%. So those low redshift objects are contributing. And in fact, when you do a dipole measurement on the low redshift objects, you actually see that they have a dipole amplitude of around 25%. They have a strong signal. And somewhat bizarrely, their dipole points in the direction of the CMB. So this could be low redshift structure, right, that is basically masking the, or adding to the cosmological dipole. But why does this structure know which direction the sun is moving in the universe, right? The CMB direction is to do with the motion of the sun, okay? And it might be that the local group direction is somewhat related to this direction, but not exactly the same. But there's something strange going on here, right? Again, when we play the game, we go through, we do the joint analysis, we find what, as we did before, the direction agrees with the CMB, the amplitudes are out by a factor of 2 to 3. So the basic summary is that there is a dipole in the distribution of cosmological sources across optical, infrared, and radio, okay? But in each of those, we're finding that the amplitude is too large by a factor of 2 to 3. And you might say, oh, maybe it's a systematic effect, maybe it's something to do with, etc. We are talking about surveys across optical, infrared, and radio. If it's systematic and it's influencing those three catalogues the same way, it's going to be very interesting. I'll just finish up by pointing out that there was a similar meeting to this one held in London earlier this year, which I attended, challenging the standard cosmological model. And I'm going to pretend to be Sabir Sakar here and point out that when we're talking about tensions, right, we talk about the Hubble tensions, it's really a few kilometers per second here or there. I know 5 sigma, etc., but it's a few kilometers per second, okay? The factor that we're talking about with the cosmological dipole measurement is a factor of 2 to 3. This is not percentage level stuff, and it's very difficult to find a systematic that will basically fix this up into the standard picture that we expect from lambda CDM. So, is the cosmological principle in trouble? I don't know, but the observations at the moment are kind of weird. And I'll finish there. Thank you.
Thank you. Are there any questions?
Thank you very much. Very interesting talk. Definitely lambda CDM is on fire. This is our job to put it on fire.
Yeah.
What I was actually missing from your analysis, but maybe I'm wrong, is that you also have a bulk flow, right? A mean motion of the sphere around us with all the matter content in there. So, and there's a couple of measurements up to 200 megaparsec with the big error bars, but they also have direction. So how the bulk flow, did you check that? How the bulk flow direction compares with your CMB dipole and with your galaxy dipole, because in a sense, if you remove local nearby galaxy structure, you actually try to subtract the bulk flow motion from that.
Yeah, I must admit, I don't know the final bulk flow direction. That's what we were looking at when we removed those low redshift things. So stuff above 0.2 should be well beyond that scale. But again, at that meeting in London, the question of just how big the local bulk flow is, and I think it was it Richard Wilkins is saying that, you know, it basically goes on forever, right? So yeah, we did a cut hopefully to remove that, and there was a signal there, but did we get rid of all of it? I don't know.
I can tell you that lambda's DM prediction is 200 kilometers per second, so definitely much lower.
Yeah.
But there are some controversial or not measurement that claim that much larger. But okay, so this is part of the analysis. Velocities are very difficult to deal with.
Yeah.
Thank you.
Okay.
Yeah, thank you for this highly interesting talk and for having shown the existence of the cosmic dipole. I'd like to know, given this existence, if you think that this will be an interesting task to try to model it with some solution with intrinsic dipole, and there is one which is the CosmoVerse model.
Yeah. The answer is yes. I think it is interesting, and I'm hopefully going to put a grant together to do some of these investigations. The problem that we have, of course, is that a little bit like we saw with the where do you take to modify your gravity today? Right? There's a broad spectrum of the kind of models we could consider. We would have to start with the simplest and work our way up. But of course, the complexity builds very quickly once you remove the basic symmetries from Friedman, Robinson, Walker, and ask what's the next general metric I can use. So the answer is yes, but at the moment it's people power and time, but we'd like to look at that in the future.
So I would like to know, I would like to learn a bit more about the following. So the Ellison-Baldwin test makes some assumption, flux limited nature of the survey, and also the radio observations where there is a spectral index, so there is a power law in the flux density. How is it applicable to optical and infrared surveys like the quasar or catalogues? Because I'm not sure about this. How you can relate what you take from radio to quasars?
You assume that you have the same sort of power law structure. So the important thing to remember is that the entire thing about the Ellison-Baldwin test is it's at the limit. It's the sample at the limit, right? So you don't have to worry about the entire population. It's just those guys at the limit. And you assume that at that point, for the small shifts that you're going to get, because it's all about shifting up and down the spectrum, that the spectrum could be represented as a power law.
Yes, but that's not true for optical or infrared surface, is it? You have a spectrum which is not a power law. It's thermal emission or dust emission.
Well, I mean, quasars are power laws, and radio galaxies are generally, yeah. So I mean,
I'm not sure.
Yeah. We can do, there's a big discussion about the source populations and whether or not population evolution can have an impact, but at the moment, it seems to come down that because we are working just at the edge of the surveys, it's only the properties at the edges, and as long as they have those kind of properties, then you should be okay.
Thank you very much for the talk. I would love to ask, because as you mentioned, after a certain distance, maybe we would expect the cosmological principle to be correct.
No, we hope.
To be held, yes. Okay. To be held as a good approximation.
Yeah.
Now, also the cosmic expansion has a strong impact on galaxies very close by. So even less than 5 megaparsec, the expansion of the universe is affecting on the Andromeda galaxy, Centaurus A and M83. Really close by galaxies, the expansion of the universe is also affecting. But in order to actually see that, you have to distinguish in between the peculiar motion and the expansion rate itself. So my question, all of the quasars that you have tested, maybe they're actually sitting on some, flow, which is actually also contributing to the results, and then it can actually resolve some of the tensions that you mentioned.
By a factor of 2 to 3?
I don't think, okay, not by a factor of 2 to 3.
Yeah,
that's true.
If this was a 10% effect, I could imagine it disappearing overnight. But we keep finding this factor of 2, 3. And I know the amplitudes are always harder to measure, and it could go down to the CMB expectation, but it's stubbornly sticking at 2 to 3.
So I would say just like comment that if you include, I mean, if there is certain, like, let's say, flow of all of these, kind of like cosmic flow, all of these quasars, and it would be possible actually to know that, you can actually improve in your results, I mean, in that.
But then if you've got a cosmic flow of quasars at high redshift, like there would be a definite direction, then you've broken the cosmological principle anyway.
Yes, but I mean also that the cosmological principle gives you, like in a low energy limit, some certain repulsion force that you can test in the local universe itself. So I mean, maybe as a principle that everything is like uniformly, that's correct, this is like breaking, but still you get certain forces that you can actually see. I mean, you get like certain force that contributes to the Newtonian force or something like that.
Okay.
So, okay.
So all that,
we can discuss.
make notes on that, that's part of your PhD now.
Okay, thank you so much. Let's take around one more time.